a cloud with sound. All right. Just quick. No. I have to use sound, and if I mute Zoom, the video on Zoom will have no sound at all. But you need, you know what? I know what I'm gonna do, I think, to eliminate Echo 360 completely. Let's see. All right. On Zoom, you're supposed to see the slide. Can you see it?
Yeah, it's just so pretty ugly. Like it's hard to read because of the angle.
Because of the angle. How about now?
Now there's just a glare on it.
How about now?
That's good.
All right. It's not good, but it's something. So, I'm going to ask everyone just quit Echo 360.
Okay.
Everyone, quit Echo 360. Let's just use Zoom today. I'm recording with sound, and it's not perfect, I believe, but it's
So
okay.
the Zoom video will have sound?
Yes, that's why we need to quit Echo 360. So you wouldn't,
Okay, thank you.
you would listen to two different sounds. So we're gonna use just Zoom today. And
And the recording will have sound as well?
that's the hope. You know what the hope is?
Okay, thank you.
So the microphone is set, the video is set. All right, let's begin this lecture officially. Again, these are the topics we will learn. And this is the calculation of the energy of a capacitor. And in this calculation, the capacitance is actually really small, just 8 microfarads, but the voltage applied is 4,000 volts, and the energy is 64 joules. It doesn't sound a lot, but let's see what it actually does with an actual capacitor. I'm a speaker. The speaker is supposed to show me, but it doesn't. It shows another student, even if it's a speaker view. All right. I still can see something there. And, the capacitor. I need muscles. Well, actually, I want to start from this small one. And I can charge it up with a battery. I just need to use plus and plus, minus and minus correctly. If the image becomes fuzzy, someone should use Zoom and say it out loud, because everything you say on Zoom now I can hear. All right. Oops, wrong. Plus to plus, minus to minus. It takes a certain time to charge a capacitor. Let's see if it's charged enough. How do I check it? Well, I can shorten it and see what's going to happen. See? Spark. What happened? Well, the energy I stored in the capacitor was very quickly released by shortening it. And that energy was actually so strong that it broke the air, and we could see small sparks. The question is, what's going to happen if I will use a larger capacitor with actually a little bit smaller capacitance, but charged by a very, very strong voltage. This is a high voltage power supply. And all I need to do is plug it. No. First, I want to connect it, because I don't want to touch leads after. It will be dangerous. In my calculation, the voltage was equal to 4,000 volts, and this power supply provides even more, up to 5,000 volts. And I will not use a tiny screwdriver anymore. I'm going to use the large one. And it says, make sure it has no charge left before you touch it again, because, well, it might kill you actually. Well, this capacitor charged with this battery gave a certain spark. So now imagine if I see how slowly it's charging. It takes time to charge. Moves slowly. More and more energy is being stored in the capacitor. 4,000 volts. 4.5. Well, good enough. I want to disconnect it. Now I need to use this because, well, now I expect a very strong spark. A strong spark means an explosion. And an explosion means a sound boom, a sound wave traveling away. And it was very loud. It's usually a very good demonstration for a morning class filled of students who napping, still, groggy. Well, what is it about? The calculation gives you a very, very small energy, 64 joules. 64 joules is like, well, if you take 1 kilogram weight and the energy, potential energy, MGH 1 kilogram times 10. So it's basically, you lift it up 5-6 meters and release it, and it hits the ground, but it doesn't make a big dent. However, if I would touch this charged capacitor with my hands, in that case, it would kill me.
Dr. V.
Because.
Dr. V.
Yes.
Could you turn off the projector screen? It's like flashing lights onto the paper, and it's pretty distracting.
Okay, just a second. How to do that? This is how to do that.
Thank you.
All right, thank you. So, it's not about the energy. It's about how fast that energy is being released. If we calculate the power, and power will be equal to this energy release over time, and it takes a fraction of a second to discharge, right? So the power is really, really huge. And what is happening? Well, when we discharge the capacitor, electrons start traveling, and those electrons start traveling in a huge amount, many, many electrons. And if I would touch it, those electrons actually could damage my tissue. But if we manage the power, we actually could use this power to do good things, yeah, to revive people. And basically, this is how it's done, a big capacitor being charged and then discharged. Well, what does it tell us? It tells us that we need to know, to study how charges travel, not just how charges being stored, but how they move. And well, this is a question to you. This is a review question. It is not a new question. We've learned it before because it's just about electric field acting on a charge in it. So lecture 8, question 2. I can actually, I can see what is happening on the other side. And I asked Boston University IT and Media Services to provide me with an extra touch monitors I could use, but they refused. I'm not sure why. So I printed out these notes in case the system would fail, and it did. And now at least we have a backup. I don't want to use the old touch screen I used yesterday because it's too old and it also might fail. It happened in the past. So from now on, I'm just going to print out slides again and again and again until Boston University IT finally will be able to do something about this situation. Right now, it's a 3rd day in a row. And maybe if you would join my plea, they would listen to you because you pay money, a lot of money. Okay, this is lecture number 8, and I want to see scores. And I want to see the summary. And I would expect that every single student will give a completely correct answer to this question. Well, not every single student, but the vast majority. To be honest, we don't even need to look at the electric field. Well, all we need to know is that negative charge has to be attracted to positive charge. That's it. But of course, we also could draw electric field lines. We also could employ a definition of electric field in this form. And we know that when the charge is negative, we just multiply a vector by a negative number. And that gives us what? a vector that has opposite direction. So the force will have to point opposite to field. And of course, in this situation, it means to the left, repelled by negative plate, attracted by a positive plate. And well, this idea tells us how can we make electrons move in a conductor. So that's the answer. And now what I need to separate slides with drawings because I can scan them in the future with slides without drawings. Okay. So this is how we can induce electric current. First, we need a conductor. What is a conductor? Anything made of metal. A wire. But then we have to generate electric field inside it. How? Well, we know how. Electric field, well, electric field strength, that's the full name, yeah? Because when we say electric field, it has two different meanings. Electric field like a substance, like change in space, and electric field like an electric field strength, this vector. So, but normally we know what it means. So this is electric field strength of this electric field. And to generate electric field strength, all you need to do is just create potential difference between 2 points in a wire or on a wire. If potential difference is not zero, electric field always points from high potential to low potential. That electric field starts acting on the electrons. The force acting on each electron feels opposite to the electric field, and electrons start moving, drifting opposite to electric field. However, people started to study electric current way before they knew about any electrons. So they actually imagined some positive charges, some fluid traveling from high potential to low potential. So historically, when people say electric current flows, they don't mean electrons move. They don't talk about the velocity of the electrons. They talk about the velocity of fictional positive charges. We could call it a positron. And those fictional positive charges would travel from high potential to low potential in the direction of the field. Hello?
Hi, it's we can't really put slides really with the picture. Is it possible to like upload them on Zoom or to upload them on Blackboard and download them and follow along?
What do you see?
Either would be good.
What do you see right now?
Oh, I see the screen and I see like a printout, but because we can't really see the words because it's too far away, it's like a little bit fuzzy.
How about now?
Yeah, that's better, but you can't see the full page.
How about now?
A little bit faster.
Well,
If you could just like upload it to Blackboard and you can download it and follow along.
I don't have a PDF file with these slides.
Oh, okay. Okay, that's better. Definitely better.
Okay, and you don't need to read the slides. You need to listen to my words and look at the pictures. Words.
Okay, well, we can't see the pictures either.
Well, can you see it now?
It's a little bit better now.
Okay. Well, let's go with that for now. Let's see what's going to happen tomorrow.
Thank you.
Thank you. All right. How about now? Yes?
Hi, Mr. D. Can I actually recommend to everybody that they go on Echo 360? Because I feel like the video on Echo 360 that shows the slides is actually clearer than what's on Zoom.
I know it's clearer, but in that case, everybody, I know it will be clearer on Echo 360, but in that case, everybody will be listening to Zoom and Echo 360.
I muted you on Echo 360, so I'm only listening to you on Zoom.
Okay.
That's what I've been doing. It's been working.
All right, so everybody, please try this. Go to Echo 360 to watch the slides, but mute me on Echo 360 to listen to me through Zoom. Thank you.
No problem.
That's exactly what you've been doing, right?
Yeah, that's exactly what I
How did you mute it on Echo 360? Please share to everybody.
So at the bottom right-hand corner, there's like the little volume sign next to sources, and I just hit that, and so it should be that volume sign with an X next to it.
At the bottom of the, which corner?
The bottom
Left-hand corner at the bottom, there is a sound dial sound control for Echo 360. So you can use that to kill the sound on Echo 360 and use Echo 360 only for watching. Thank you.
No problem.
All right. But I need to use sound on Zoom because I want this video to have the sound. You don't want just watching the slides. And well, Echo 360 recording should have both the sound and the slides. Well, go ahead. So let's move on. Fictional positive charges. This is what technically we should imagine every time when we need to figure out what is happening inside a wire. We pretend there is a positive charge and we can analyze what will be happening to it. We know a positive charge would travel from high potential to low potential in direction of the electric field, and this direction is being defined as direction of electric current. Even the actual direction of electric current in a wire is opposite to this field. Actual electrons move that way. Well, we just need to remember. Now, how can we measure the strength of this flow? It's like a fluid, but made of charges. Well, this is how the definition of electric current strength, or just electric current, is amount of charge traveling per second. I can write it larger, Q over T, basically. This is the first new physical quantity we need to remember. Now we can solve a problem. So we have a battery, and a battery may be attached to, well, calculator screen, display. There's electric current traveling, and the electric current is given, this new variable I is given to us. What does it say, MA? Well, if you look at the definition, the unit of electric current should be equal to a coulomb over a second, and that's what we call amps, or just A, amperes. And this is milliamps. So 0.17 times 10 to the negative 3 if you use International System of Units. The question is, how many electrons run in an hour? Okay, so what do? The definition says that this electric current should be equal to the ratio of total charge traveling over time. So I can calculate total charge traveling in 1 hour. I just have to multiply two numbers. electric current and time, which is 0.17 times 10 to the negative third times, well, we have to use seconds, and 1 hour is 3,600 seconds. But that's the charge. How can I calculate the number of electrons? Well, exactly the same way we did it before. This charge is due to n electrons traveling, right? And each electron carries the same charge. We call it elementary charge, and it equals to magnitude of, well, 1.6 times 10 to the negative 19th. So to calculate the number of electrons, all you have to do is this. And you will finish it later. We've lost already too much time. This is a very simple calculation. Actually, I have it. Well, if I had an object, any object, acted upon a force, just one force, this force would have been net force. That means this object would have be accelerating. The acceleration would not be equal to 0, PY105. What does it mean? It means it would have been traveling faster and faster and faster and faster and faster forever. But that is not happening inside any conductor. Electrons cannot accelerate and travel infinitely fast. And that is not happening. Why? Because inside every conductor, we have more things than just electrons. We also have many, many nuclei, and each electron collides. And when it collides, it bounces off. So we have a huge nucleus, a tiny electron hits it, and then bounces back. Of course, it loses some energy. This huge nucleus starts moving a little bit faster. And actually, what does it mean, moving faster? When atoms move faster and faster, that means kinetic energy increases. And we know that it means, from PY105, it warms up. Temperature should go up. And we'll talk about it later. But in general, right now, all I want to say, electron hits, bounces back, and slows down because of that. And this happens a lot. So if I look at the graph for the speed or velocity of electrons as a function of time, well, I want to use speed, it's easier. So electric field picks it up and it accelerates, but then bounces back, slows down, accelerates again, slows down, accelerates, slows down. So on average, it travels at certain constant speed. It drifts. We call it the drift velocity. And this drift velocity is the reason of the existence of atoms. Now, in reality, actually, electrons drift very, very slowly, about 1 millimeter per second. So if you flip a switch at home, the light comes up instantly. Why? It is not because electrons travel from a switch to the bulb. You close the switch and the bulb is on immediately. But it's not because this electron is so fast so it gets to the bulb immediately. No, it's because when we close the switch, electric field is so fast that it starts acting on all electrons simultaneously, and they all start traveling, but very slowly, but immediately all. So let's take a look at this process. We've got an electron. So there is a force acting on this electron from electric field. The magnitude of this force is charge times field. An electric field is proportional to potential difference between two ends of this wire. There's a wire. We apply. How do we create potential difference? Doesn't matter, but normally just a battery. So we've got a high potential on one end and we've got a low potential on another end. And this wire is long. So what is happening next? Because of the collision, on average, those collisions create a force of, well, resistance that cancels out the electric force. That is why net force on average is zero. That is why the velocity on average is constant, drift velocity. But what about this velocity, this force? Well, in general, we could again just apply our common sense. If electrons would travel faster and faster, they would experience more collisions, and that would lead to more resistance. If they travel slower, that means they experience less collisions, and that would lead to less resistance. So this force is in a way proportional to how fast electrons travel. So we could imagine that there is some kind of a coefficient, I don't know, C, coefficient. And now we are in troubles. Why? Because this V represents potential, and this V represents velocity, and we need to remember which is which. I don't know, maybe I do it a little bit differently. Well, what does it mean? It means that when net force on average is zero, velocity is supposed to be proportional to electric field. Or that means it would be proportional to potential difference. Inversely proportional to the length. And if we have large value of potential difference, that means electrons will travel fast. Well, no potential difference, zero, no motion. And if we have many electrons traveling fast, that means electric current also related to potential difference. Faster electrons means higher current. So electric current should be proportional to potential difference applied to the wire. No potential difference, no electric current. Higher potential difference, higher current. And this is the law that was experimentally derived by physicist Ohm. So this is how we can write it mathematically. Potential difference and electric current proportional with some coefficient. This coefficient, of course, supposed to depend on the structure, on the size of the atom, of the density, and other things, and also at the length. And the more accurate calculations tell us that this coefficient depends on the area of a wire. Why? Well, because if we expand the area, we give more room for electrons to travel, more room, less resistance. And it proportional to the length, longer wire, more atoms, more collisions. So what we have here is the law that has a name of Ohm, Ohm's law. People write it differently in the form of a ratio or in the form of a product. Well, we like product better. So the Ohm's law says potential difference of voltage across a wire is proportional to electric current through that wire. And the coefficient depends on properties of this wire. This coefficient has a name, the resistance. And the resistance is proportional to length, inversely proportional to area. And that coefficient has a name resistivity, and that you can look it up. Just Google resistivity of copper, you get one number. Resistivity of aluminum, you get another number. So this is what we need to remember. And another important statement, I said several times that electric current, those fictional positive charges, travel from a higher potential to a lower potential in this direction. So we don't really have to write absolute value every time. We can write just the difference, but we need to remember which is higher, which is lower. And this is an example from Google, resistivity of copper. That's it. We don't need to use this equation, but we really need to understand how the Ohm's law works. And for that, we need to solve more problems. So calculate potential difference. Again, remember, potential difference between is also the same as voltage across. Yeah. Different names, the same meaning. It is equal to higher potential minus lower potential actual difference. So between the ends of a wire has a given resistance. So we don't really care how wide, how long it is. We already given this number. And I didn't mention that because of the Ohm's law, the unit for this variable R, resistance, has a name, ohms. So 10 ohms. And in physics, there are two different symbols for ohms. This capital omega, a Greek letter, or people just write OHM, ohms. So, or else? We know that every minute, that means 60 seconds, 360 coulombs travels through this wire. All right, done. Well, what I could add, I technically don't know the direction of a current, but I could add it. Let's say it travels to the left. In that case, I can make a statement that this end of this wire should have a potential higher than this end. But I also know that if I would have an electronic microscope and I would look at, I would see electrons traveling, actual electrons traveling in opposite direction. Again, remember, this is a direction of the motion of fictional positrons. They don't exist. This is basically the direction of the motion of electric field. It points from high potential to low potential. All right, review. Well, now we just have to combine these equations and calculate delta V. So delta V equals current times resistance, but current equals charge over time. And again, it's a very simple calculation. I'm not going to do it. I'm going to read the problem. The filament in this bulb, probably just a bulb inside a flashlight, is a resistor. Yeah. Everything what is not a battery is a resistor. So the wire becomes hot enough to make it bright, to lighten up, and the electric current traveling through this wire is given 0.4 amps. But in order to do that, we are applying two 1.5 volt batteries. So there's a battery number one, 1.5. There's a battery number two, 1.5. We need to calculate the resistance. Well, this is a good place to actually try. show something. Now, since you don't need to look at the slides, I can unmute and actually zoom out. All right. I've got some toys I can play with, and save this on Zoom, and I want to save this on Echo 360. Well, I need now just some wires, and let's play. Yeah, well, shadow. We do our best. First, what is the simplest circuit? The simplest circuit has a source of a fixed potential difference, a battery, and a resistor, for example, a bulb. Of course, electrons cannot just jump from an electrode, from a battery on the electrode of the bulb. So we have to use conductive wires. They look insulated. They look like a plastic, but we know inside we've got copper. All right. So I have to make a connection. Done. Well, why nothing is happening? Because those electron or fictional positive charges, they stuck here and they cannot jump. So we have to use another wire to complete the circuit. And now we can see the filament is on, bulb is on. Because I know I can read the value for this voltage, 6 volts. And I can, well, I buy it, so I can read description. I could, for this bulb, the resistance, I think it was like 5 ohms. I can calculate electric current right now. All right. I can actually take a look at those positrons. This device shows you those fictional positive charges. Again, I just need to complete the circuit. And you see electric current. Well, you don't see, but I can see plus. This is a plus. So fictional positive charges, like skiing down a hill, they would travel from high potential to low potential outside of the battery. So they would travel like this, like this. This is fictional positive charges, not electrons. Actual electrons would travel in opposite direction. And this is a constant electric current. Now, how can I change it? Well, I can add another element. This is a variable resistor. It's basically a wire wound up on a cylinder, and by moving this movable piece, I can change the resistance. More wire, more resistance. But now, of course, I need to connect this into the circuit. So I have to break the circuit now and connect this to this electrode. And I'm imagining how would electric current travel. Electric current would travel here, 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 here. But now I need to connect these two electrodes. Electrons cannot jump, so I need another wire. And now I can increase the length of the wire in this variable resistor and see what's happening. These start traveling slower, bulb becomes dimmer, because when I make wire longer, I increase the resistance, make it higher and higher, and that makes electric current lower and lower. It's still not zero, but it's not enough anymore to warm up filament, to make it hot enough. And eventually, the resistance is so large that electric current is practically zero. All right, this is not yet the problem we need to solve. In our problem, we have two batteries. Okay. I've got another one. And so again, I need to, all right, like close the circuit. Now we need to connect this. What happened? What's wrong? I have two batteries. It should be even brighter than before. Well, turns out the connection matters. You see, middle to the middle. I connected a minus to a minus and a plus to a plus. So what does it mean? Just for a second. So I have two batteries, and I connected these batteries like this, a minus to a minus, and a plus to a plus. There's a resistor here, a bulb. This is a standard symbol for a bulb, and nothing happening. Well, the battery is manufactured in such a way that no matter what we do to it, it provides fixed voltage. Well, this battery provides 6 volts. But if we look inside the battery now, we would see electric field. Electric field should point from plus to minus. And inside this battery, electric field also points from plus to minus. So, of course, if we have two identical batteries, electric field strength number 1 is equal to electric field strength number 2. And as we know, superposition principle tells us to calculate net electric field, we just need to add as vectors, and they cancel each other out. That is why in this situation, even we used two batteries, nothing happened. But now we know what to do. We just have to connect these batteries in series, in its natural sense, a minus to a plus, and then connect it through the bulb. And in this case, this electric field plus this electric field gives stronger net electric field, which means total voltage will be equal to the sum of voltage 1 plus voltage 2. And now we can solve this problem. Now it becomes trivial. So now we know what to do. And then now, what do? Do I want to do more experiments? Yes, last experiments with two batteries connected in the right way. So now I know what to do. I need to connect opposite electrodes. So minus and a plus. Minus and the plus. And now, well, actually, I can use the switch. Just one more element. What is a switch? A switch is a broken wire that can be easily fixed. When the switch is open, electrons cannot jump across, and that means the resistance is infinitely high. But when I close the switch, the resistance becomes practically zero. this wire is so short that it's basically resistance less. And this is also resistance less. For every circuit, practical or theoretical, we always neglect the resistance of each wire. Technically, it's not zero, but the only resistance we use is the resistance of an actual element, a bulb or a motor or a heating element. Battery also has no resistance for us, ideal battery. In reality, it does, but we neglect. The battery is just a source of a fixed value for voltage, for potential difference. All right, open, close, open, close. I could do it forever. Now I need to go back to original setup to finish calculations. So what do I need? I need to zoom in again. I know how to do it. More, stop. And shift to the right. Now I need to mute the screen. Now I need to lower the camera. Why can't I see? See myself. All right. More or less. So now we just have to finish this calculation, draw the circuit. And in my picture, the bulb is connected to these batteries. These batteries already have correct connection. And I know now that 1.5 plus 1.5 gives total voltage of 3. So I can replace these two batteries with one which has voltage of 3 volts. And the bulb, so electric current travels how? Well, we know this long line represents a high potential. This short line represents a low potential. Low potential always can be set to 0. It's like potential energy always can be chosen to 0 somewhere. And basically, we say that here electrons have 0 potential energy. In this case, this electric potential will be higher by 3 volts. 3 volts plus 0. And well, we have to apply the Ohm's law. To what? We actually could apply Ohm's law to a wire. From here, from this point, let's call it A, to this point, let's call it B, there is a certain wire. So the voltage between A and B should be equal to current between a resistance between A and B times the current between A and B. But as we said, the wire has no resistance. That means there is no potential difference between points A and B. It's a very important fact. There's a slide which says this: a wire does not change potential. So if my electric potential here is 3 volts, until wire, doesn't end, it is always everywhere potential equal to 3 volts. So potential B is also 3 volts. And same here, if this potential is set to 0 and wire does not change potential, electric potential here at point C is also 0. So 3 volts, 0, potential difference between points B and C, which is voltage across the bulb, is 3 minus 0, 3 volts. And of course, it has to be equal to current times resistance. And this is how we can calculate resistance. The current was given 0.4 amps. So R equals 3 over 0.4. Two slides. I don't know why. Done. All right. Finally, another question to you, so I could drink some coffee. This is the simplest circuit which could be done when we have everything we need: battery and resistor. Now, so you are looking at this circuit and choosing your answer. Right here, I'm going to draw it larger. So right here, we've got a battery, and the electric potential here is set to 0, And there is some kind of a weird symbol, EMF, and it says 6 volts. And then there's a box. There is a box that represents a resistor. We've got different symbols for resistors. And the question is, what is the value of electric potential here? Well, first of all, what does EMF mean? EMF means electromotion force. Now we have to forget it, because this term came from the history. People actually thought that when the Volta discovered how to generate electricity easily, people thought that some mechanical interaction is happening inside, and that interaction leads to moving electrons or charges in general inside the battery. So these are possible answers. So this is question 3. If you think 1 volt, choose 1, 2 volts, choose 2, 3 volts, choose 3, etc. So people called that force that has to move charges inside the battery from one electrode to another, they called it electromotive force. Now we know there's nothing like that. Now we know that the reason for this potential difference is chemical diffusion. Now we know that inside this battery, there's different ions traveling in different directions. And basically what they do, they pick up electrons from one electrode and they diffuse to another and they release that energy there. So inside each battery, you can imagine some tiny demons traveling on both, and they pick up an electron from here and then move it over here. Those tiny demons work hard because they have to work against electric field. Again, remember, this long line represents positive electrode, and this short represents negative electrode. That means inside the battery, electrons have to travel against the force. If this green letter and arrow represents electric field strength, the force from electric field on these electrons, I'm saying it, I don't know, 10 times, the force should point opposite to field. But those tiny demons, we call them diffusion. they actually make electrons move against the force. That's how battery works. Outside of the battery, if you release an electron here, in that case, it starts traveling like it's supposed to. Electric field outside of the battery also points from positive to negative charges. That's electric field outside. And this electric field, of course, acts on electrons like supposed to. So this is the velocity of the electron, but fictional positive charges, they would travel like this. This is the direction of electric current. Well, now I want to check your answers to the web assignment, because basically this is a kind of a short memory test. I just told you that a wire does not change potential. So this is that constant voltage the battery provides. Just a different name for it, EMF. So you can say EMF of this battery is 6 volts. Okay, you know, it means constant voltage provided by this battery between these electrons equals 6 volts. That's it. And if this potential is set to 0, this potential V plus should be equal to low potential plus voltage, 0 plus, well, there is another symbol for EMF, a Greek letter epsilon. Now it's EMF, not dielectric constant or something else. So plus 6 volts. So electric potential here is 6 volts because that's what the battery does. But a wire does not change potential. That means electric potential here also should be equal to 6 volts. And the electric potential here should be equal to 0 volts. So voltage across this resistor should be equal to 6 minus 0, 6 volts. And 6 is the winning answer. Good. So just remember, wire has no resistance. That's why a wire does not change potential. And EMF, or epsilon, is just a fixed value for voltage provided by the battery. All right, I just did this. Well, this is just, again, why a wire does not change potential. Because for a wire, the resistance is 0. And even if electric current is not 0, a wire does not change potential. What changes potential? Well, of course, battery. Battery increases potential by the value of EMF. What else changes potential? Of course, the resistor. But the resistor decreases, or people say drops, the potential in the direction of electric current. From here to here, electric potential drops by 6. This. That's why we also use different names for batteries and resistors. A battery we call an active element. Something active happening inside. Demons, diffusion, demons make electrons travel against the electric force. But there is nothing inside this, just wobbling atoms. So that's why a resistor also has a general name, a passive element. Question. I want to ask you this question, but probably the last for today. We've got 15 minutes left. You already know the name for this type of a wiring. We call it in series. Now, these elements, not capacitors, these elements are resistors, bulbs. This symbol is a standard symbol for a resistor. And we have them both connected to battery. We can imagine that we've released a positive, fictional positive charge here. Outside of the battery, it should travel away from positive charges. So electric current travels through the wire, through the first resistor, through the second resistor, back to the battery, but also doesn't stop, keeps traveling. So outside of the battery, electric current travels from plus to minus. Inside of the battery, the same electric current travels from minus to plus. Well, I'm just stalling. I'm giving you a chance to answer this question by choosing one of these answers. What do you think is the same? Resistance, current, voltage? Why do I care only about these variables? Because the Ohm's law relates only these variables. However, when we write this equation, we need to know, first of all, the exact meaning of each variable. Is this potential? Well, technically, V is potential, but the whole thing is voltage. What's I? Electric current. R, not a radius, resistance of what? And this is, again, a very important statement. This is the resistance of the element for which you're writing this law. And you can write this law for this element. You can write this law for this element. You cannot write this law for the battery because our battery has no resistance. And when you write this law, you need to make a statement in this circuit. What is the same? And this is actually a common sense type question. Because again, if you look at these fictional positive charges traveling through the wire, they enter this resistor at one end, and they all leave this resistor on another end. They do not disappear, not get leaked away. And also, we have no additional sources. We may have another battery, but it's not connected. So the resistor does not change the number of electrons traveling through, and the same electrons now keep traveling through the second resistor. And basically, electric current is like a charge flow rate. That's what it is. And the charge flow rate, of course, here should be the same for both. In this situation, the electric current has to be the same. Well, what does it mean? How can we use it? Well, technically, we can write two laws. Two Ohm's laws. Delta V1 should be equal to I1 times R1. Delta V2 should be equal to I2 times R2. But the electric current is the same, so there is no need to keep the subscript. Okay, how can we use this? Well, actually, we also know now. It doesn't matter if we have resistors or capacitors, it's about potential difference. So potential difference from here to here, which is provided by the battery, has to be equal to the sum of these two potential differences. This is actually nothing new. Potential difference number 1 plus number 2 is equal to the total potential difference provided by the battery here. Now what can we do? Well, now we can ask a question and answer this question. What would be the single resistor we could use to replace these two, but having the same current when that resistor is attached to the same battery? This is an equivalent resistor or in series, and we use the same battery, so the same voltage, and we want the same current. That's why we call it equivalent. But now for this circuit, we could write the same law, delta V should be equal to this current times equivalent resistance. And I'm do the math. It's very simple. We've done it before for capacitors, exactly same mathematics. And the result is, because the electric current is the same, I just did it. I have extra slides. This is the result. When we have several resistors connected in series, we always can replace them with one single resistor, which has equivalent resistance, which is equal to just the sum of all those individual resistances. And now we know this. And now the circuit is happy. See? It was sad. Now it's happy. Well, of course, we need to analyze a connection in parallel. That's not a Weber-Stein question. And of course, we know what to do, because of course, we know that now potential difference, the voltage will be the same for all of them. So potential, electric potential number one, electric potential number two, this one is higher. The difference, delta V, is just equal to EMF of this battery, or epsilon, wherever it is. But as we know now, a wire does not change electric potential. So the same electric potential will be here, 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 and then here, 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 here. The same. This is why we could always redraw or rewire a circuit in this way. It doesn't make any difference. It doesn't make any difference because physically, electric potential is the same no matter if we wire it one way or another. V plus, V plus, V plus, V plus, V plus, V plus. And of course the same V minus, V minus, V minus, V minus, V minus, V minus. So what we need to write now is delta V1 equals delta V2 equals delta V and what else can we write? Well, 2 Ohm's laws, one for each. Delta V1 equals I1 times R1. Delta V2 equals I2 times R2. Can we say now that the electric current is the same? No. You see what's happening with electric current when it moves away from a battery. It reaches splitting point and then it splits. So electric current traveling through the battery splits into two. Okay, first of all, again, we know that in reality, there are actual charges that being split. But the total amount of those charges cannot change because we don't put any extra charges and we do not destroy them. And charge per second is current. So if I add a charge number 1, oh, okay, and the charge number 2, I should get the total amount of charge traveling initially. And if I divide it by time, I get a very important connection between these 3 currents. The current number 1 plus current number 2 should be equal to the original current. And actually what happened next? Well, they split here, but they combine again after. And basically this is the law of conservation of electrical charge. All right. What else is missing? Well, of course, we want to find what single resistor can we use to replace these two. Right, we have to continue. So my equivalent circuit, again, should have only one battery and only one resistor. But that resistor should have a new resistance equivalent or parallel. What does equivalent mean? That means right now, if I connect it to the same battery, I should observe the same current. The same current where? Well, of course, through the battery. This current through the battery should be the same, big I. And of course, now I also can write the Ohm's law. This delta V should be equal to this R times this I. And now I have what? 1, 2, well, same delta V, 3, 4, and let's call it 5. 5 equations. And we can solve it. And we've done it before for capacitors. This calculation is no different than before. Symbols are different. But the result is what? Well, first of all, remember the voltage is the same. Second, remember electric current splits. But here at this splitting point, or we call it a junction, we can apply the law of conservation of charge. Also, now we call it differently. We call it the junction rule. And if we apply the junction rule combined with Ohm's laws, junction rule, Ohm's law, for any number of resistors connected in parallel, for any number, the result is wait for that. I'll keep you in suspense. This is the result. This is the calculation, and this is the result. For resistors connected in parallel, the equivalent resistance can be found using inversed resistances. So we've done it before for capacitors connected in series, and done basically with almost done with theory. This is just something that helps to visualize what might be happening inside the circuit. Remember, I mentioned several times, a battery is acting like a pump. So you can imagine the pump, pipes, and electric potential is an equivalent of a pressure here or pressure there. And there's a pressure difference that pushes water through. And depending on connection, series, parallel, we can trace pressure or potential, and we can see what's happening to charge or current. Here it splits, but combines again, and here it's the same everywhere. All right, this is the summary, things to remember. Ohm's law, electric current, and junction rule, and connection in the parallel and series. And the last slide for today, again, just a summary. What should we imagine? What's happening inside? Yeah, an active element, a battery. A battery actually is a complicated device, active device that moves electrons against the electric field. But outside of outside of the battery, charges just travel like they're supposed to. Atoms slow them down in a way, but a wire has no electric field inside. Electric potential is constant, and charges just travel by inertia. And if we have one battery, we can always set electric potential to 0, the lowest one. Done for today. Good luck with the lab. And I'll see you tomorrow. And I've got more slides left. Okay, thank you. Have a nice day. And goodbye.